So welcome to everyone here to the FACS meeting, Formal Aspects of Computing Science. My name's Jonathan Bowen. I'm the chair. I think I know most of you, but in case anyone new is there, welcome. Today it's a completely online meeting, and we've got Professor Abbas Adalat, who's at Imperial College. He's Professor of Computer Science and Mathematics since 1997. Previously, he was at the Sharif University of Technology in Tehran, and he did his PhD at Warwick University in the UK. He's got varied interests, all sort of formal methods related in a way, including exact computation in differential and integral calculus, computational geometry, computation in logical form, optimization theory, game theory, and computational psychiatry. And he heads two groups at Imperial College, the algorithmic human development, and the continuous data types and exact computing research groups. So today he's going to talk about soft models for probabilistic computation, which hopefully most of you in the audience have heard of Dana Scott, who's very well known in formal method circles. And he's going to report on joint work with a colleague of his who's, I think, in the audience, but he'll tell us more about his collaboration with Pietro. So over to you, Abbas.
Thank you very much, Jonathan. So let me share my screen. So I suppose it is shared now.
You make it full screen, that'd be great. Looks good.
Okay. Well, thank you to the organizers for inviting me to this seminar series. So I'm going to talk about Scott models for probabilistic computation. It's joint work with Pietro Di Gianantonio from University of Udine. In this talk, we are giving a solution to a long-standing open problem in semantics, denotational semantics of programming languages, namely to develop a Scott model for probabilistic computation. This has been an open problem since the 1980s, and I will explain more about this later on. So the outline of the course, of the seminar is as follows. We want to develop a model of probabilistic computation based on Scott domains. So Scott domains were introduced by Dana Scott, as I will explain later, and they form a very prominent first example of denotational semantics for programming languages. And our model satisfies the following key conditions. Firstly, it is based on fundamental notions of probability theory and denotational semantics. So essentially, we are not introducing any new concepts to develop this Scott model or these Scott models. And the model supports a computable framework. So it is based on an effective structure of these Scott domains. And it would give rise to the construction of simple and practical monads for functional programming languages, monads like maybe, list, power set, etc. Okay, so let's start with elements of probability theory as introduced by Andrei Kolmogorov in 1933. I could only find one colored photo of Kolmogorov, which is the one that I have here on this slide. And it's also the only photo in which he's smiling. So I chose this one, although the quality is not great. So the contribution of Kolmogorov to probability theory is quite crucial because for almost a century, it's had the test of times. His axiomatization of probability theory, his consistency conditions for stochastic processes is and are the standard notions in probability theory and stochastic processes. It, of course, predates modern computer science, and it's been fundamental in many branches of science. In computer science, it plays a key role now in machine learning, deep learning, especially in the past 10, 15 years. Essentially, the major revolutionary breakthrough in machine learning and deep learning is based on probabilistic computation, but also in robotics, quantum computing, in all kinds of modeling, cognitive sciences, and other branches of computer science. So let's just have very, very basic notions of probability theory that we need in this talk. So Kolmogorov introduced the idea of a probability space as a sample space A. So A is just a set together with a collection of distinguished subsets, sigma A, that he called events. So this is a sigma algebra, which means that it's closed under countable union, countable intersection, and complementation. And there's a probability map, nu, from this set of events to 0, 1, such that the whole space has got mass 1, weight 1, probability 1. And the probability map is sigma additive, which means that for a finite or a collection of countable disjoint sets, SIs, the probability of the union of these disjoint sets is just the sum of the corresponding probabilities. So very, very basic axiomatization of probability theory. So usually in mainstream mathematics, the sample space is taken to be the unit interval 0, 1, subset of the real line, and the sigma algebra is generated by open intervals of the topology of the unit interval, the Euclidean topology. And for the probability distribution, one uses the uniform or the Loebach distribution that we denote by nu. But in computer science, we usually take the sample space to be the infinite streams of bits, zeros, and ones, which is denoted like that. And the sigma algebra is generated by open cylinder sets. So these are, so we fix the first, say, n elements of an infinite string, x1, x2 to xn, so they are fixed. And we look at all the streams that start with this initial segment. So that is an open set of the Cantor topologies. So this is the Cantor space on 0, 1. And the uniform distribution on the bit 0, 1, so allocating a half to 0 and a half to 1, is gives rise to the product measure. So it gives a probability distribution on the whole sample space. And all we need to know about that is that the cylinder set, so the set of streams starting with a fixed finite set from x1 to xn, has got weight 2 to the power n, n being the number of fixed bits in this collection of streams. So I'm using the same notation, nu, for the Loebach measure, the uniform measure on 0, 1, and also the uniform measure on bit 0, 1 extended by product measure to the whole space, because we are going to present more than one monad, and having the same notation nu, both for the probability distribution on 0, 1 and for the Cantor space, space of infinite streams, allows us to deal with these monads uniformly. All right, so that's the sample space. So what's a random variable? So a measurable space X is a space with a sigma algebra, a set of distinguished events, subsets of the space. And a random variable on X is a measurable function, R, from the sample space A. So A is one of the canonical sample spaces that I presented in the previous slide. So we have a map from sample space into our measurable space X, such that the pre-image of any event is an event. So the pre-image of any distinguished subset of X, which are called the measurable sets or events, is an event in the probability space. It's very simple. It's a bit like a continuous map. Instead of using open sets to say that the inverse image of open sets is open, we say that inverse image of events are events. And the probability of an event in the measurable space X is the probability induced by that random variable R. This is called the push-forward measure, the push-forward probability distribution induced by R. Well, and it is this. It is just nu of the inverse image of the event B. And it is the probability of the event R minus 1B as determined by nu, or the induced probability of B that R induces. And the key observation here is that different random variables can correspond to the same probability distribution. So if you have got two random variables, R1 and R2, from a sample space A to a measurable space X, they are said to be equivalent if they induce the same probability distribution. Namely, if they induce the same probability weight on any event B, for be an event of the measurable space X. So this is all we need in terms of elements of probability theory in this talk. So next, elements of domain theory that we need in this talk. So Scott domains were introduced by Daniel Scott in 1970 when he was at Oxford, and famously this led to the D-infinity model of untyped lambda calculus. So this is a partially ordered set, the infinity, which is isomorphic to its own function space. So it's a particular partial order. It's a Scott domain, which I will define in a minute. And it's got this key characteristic that it's isomorphic to its own, is homeomorphic to its own function space. So of course, this generated a lot of interest in Scott domains. It gives rise to a Cartesian closed category that I assume that you know, like category of sets with objects, sets and morphisms, functions between sets. And the Cartesian category is one for a concrete category in which the home sets, namely the functions between objects, are just sets. It's just this one-to-one identification between the home set of X times Y, X and Y being two objects, and the third object Z, and the home set of X and Z to Y, which is the exponential, or as we can regard it here, a function space of Y maps from Y to Z. So if this is a one-to-one mapping that is natural in X, Y, and Z as three objects, then we have a Cartesian closed category that allows currying to take place. Anyway, I think most of you are familiar with these notions, but in case some people are not, just had a very brief review. So Gordon Plotkin in 1977 developed a simply typed lambda calculus based on Scott domains, and this led to the paradigm of programming language for computable functions, PCF, which has been a very active area of research in the past few decades, still a very active area of research. All right, so let's just have elements of the Scott domains technically, because that's what we need in this talk. So a bounded complete DCPO with a finite tree approximation. So in a directed complete partial order, so we've got a a set together with a partial order, and the set is directed complete. So any directed set has got a supremum or least upper bound. So the way below relation, so this is famously defined by Dana-Scott, or the finite approximation of an element B to another element A, is defined as follows. So B is way below A if for any directed set of elements Ci, I belonging to an indexing set I, whenever A is bounded by the supremum of these elements, supremum exists because we are taking a directed set, then one of the elements in this set, in this directed set, already is dominating B. So B is bounded by an element in this directed set. So the intuition for Dana-Scott here is that the Webber-Roach is a finite approximation, because we can think of these CIs as finite computations, and the totality of the information that we have, which is captured by the supremum of this directed set, if that totality, if that total information dominates A, then at some finite level, some finite computation in our directed set must dominate B. So that's the notion that he defined, and he was motivated by various examples in analysis, and we will come to that in a minute. And then he said that B, if you have a subset of this CPO, it will be a basis if for any element in D, if we take all elements in B that are way below A, they form a directed set, and the supremum would be A. So every element in this DCPO can be generated by basis elements way below it. So approximated in a finite tree way by the basis elements. And then he defined a countably based DCPO. So a DCPO that has got a countable basis to be continuous, or in today's terminology, we just call it a domain. So a simple example is taking the set of natural numbers and adding a bottom element. So this has got two levels, bottom and all natural numbers that are on the same level. So this is a Scott domain that we will define in a minute, but in particular, it's trivially a continuous DCPO or a domain. And then the Scott topology, named after Scott, which we denote by capital omega D of a continuous domain, takes a very simple form. You take any basis element B, and you take all the elements that this basis element approximates in a finite tree way. So all elements A that are way above B, or B is way below A. So that forms the basis of Scott topology. And now a Scott domain is a bounded complete domain. So bounded complete means that any bounded set has got a least upper bound that is denoted by supremum of that set, or Scott used this notation, but I'm going to use supremum rather than that, which is more in the tradition of mathematics. And the key important issue here is that Scott domains can have an effective structure. So you create an enumeration, effective enumeration of the basis elements, and you stipulate that this is going to be recursive, that this enumeration gives you a recursive set for the way below relation. So that gives you an effective structure for the Scott domain. Using that, you can define computable elements of the Scott domain, and also computable elements of the function spaces that we will come to in a minute. But now let's have a more sophisticated example of Scott domain. I should open a bracket here. So in semantics, Scott domains are usually regarded as algebraic Scott domains, namely those that have got a basis in which every element is way below itself. These are called finite or compact elements. But in this talk, because we are trying to bridge between classical probability theory and the notation of semantics, we are going to use continuous domains, not algebraic domains. So I'm not discussing algebraic domains at all. By Scott domain, I mean a continuous Scott domain. So a prototype example of Scott domain is the domain of intervals. So take bounded closed real intervals and order it with reverse inclusion. So here's the thing. So we have got this set of real numbers. These are singletons. They are the maximal elements of this partially ordered set, because this partially ordered set consists of closed intervals. So for example, A here is a closed interval from a real number A1 to real number A2. So A1 is this real number metaphorically, A2 is this real number metaphorically, and the number pi is, for example, sandwiched between these two numbers. So this interval, so think of it at 3 and 4, the interval 3, 4 is an approximation to the real number pi. And if we go up in the approximation order, we get a better approximation. For example, this point could correspond to 3.1 and 3.2, which is a better approximation to pi. So this forms a Scott domain, this simple partially ordered set that every mathematician can actually identify with, because these structures, not with this particular name, but the properties are used quite often in analysis. So if you take a directed or bounded set of intervals, then the least upper bound of the supremum is just the intersection of these intervals. So that's very well known in analysis, that the intersection is non-empty and exists. It will be an interval. And the basis of this Scott domain will be just the rational intervals, because we want a countable basis. So we just take rational intervals. So this should be Q1, Q2 in Q, and they form a basis. And the way below relation is that we have got an interval B1, B2 way below A1, A2 if A1 is strictly bigger than B1 and A2 is strictly less than B2. So in a sense, A1, A2 should be in the interior of this interval. So that's the notion. And I think that was one of the motivation for Dana Scott to abstract from this property of intervals to deduce the notion of way below relation for partially ordered sets in general. And the basic Scott topology in this simple partially ordered set is that, so you just fix a rational interval B1, B2, and you look at all the rational intervals, you look at all the intervals that are in the interior of this rational interval. And that forms a Scott open set. So it's a picture, and as I said, going upwards gives you the direction of increasing information. All right, so the function space for Scott domains is quite simple to construct and is essential for Scott domains to become a Cartesian closed category. So suppose D is a Scott domain, and suppose X is a topological space with a continuous lattice of open sets. So X could be a Scott domain itself, or it can be any of the standard probability spaces that are introduced earlier on in this talk. So it could be the unit interval 0, 1, or it could be the Cantor space, infinite streams of bits 0 and 1. Then the set of Scott continuous functions from X to D, so we use any topology that X has come up with, which has got a continuous lattice of open sets. So the lattice of open sets for a topology can be a continuous domain with the properties of a continuous domain that I explained. So if we have got that topology on X. We take the Scott topology on D, and we look at all the Scott continuous functions from X to D, and we order it pointwise by the ordering induced from D. This gives you an ordering on the functions, and this gives you a Scott domain itself. So this is a very simple and important construction, and the key ingredient here is a step function. So a step function is a function which takes only a finite number of values. So a step function from this space X to this Scott domain D is obtained by taking a finite number of open sets in X and a finite number of, let's say, basis elements in D, and taking this supremum. So we require that they form a consistent set, that the supremum exists, and the supremum would be a step function. And the value of this step function at each point X is just taking all the DIs that for which X belongs to the corresponding open sets OI and taking the supremum. So it's a simple construction. It allows for the construction of the function space, and it also gives a basis for this function space, and this leads to a Cartesian closed category. All right, so now let's go to the next section, which is monads. So I'm having this slide to stress the point that for non-deterministic programs, for non-determinism, in the 70s and 80s already this problem was solved in terms of denotational semantics based on the Scott model. So like the power set monad, there are three basic power domain monads for non-determinism for a domain D: the lower Hall power domain LD, the upper or Smith power domain U of D, and the convex Plotkin power domain CD. So in all these three, the basis of these domains, these new domains that we create as power domains with the underlying domain D, consists of finite subsets of D, but with different ordering. And the CC of Scott domains is closed under the lower power domain functor and the upper power domain functor, but not under the convex Plotkin power domain functor. But the Plotkin power domain functor has got disclosure property for the bifinite domains. That is a bit more complicated to define. I'm going to skip that because we don't need it. I wanted to have this slide to say why we should take the spirit of these power domains in terms of constructing a monad for probabilistic computation. So the spirit of these monads for power domain construction is that there are functions, there are multi-functions, but there are still functions in a sense. So for an input, they can result in a number of outputs, but it's a multi-function. So the probabilistic power domain of a domain, and by domain I mean a continuous DCPO, it was introduced first by Saeb Jahromi in '79 when he was a postdoc at the Edinburgh, and so the elements of it was introduced by him. And some 10 years later, a student of Gordon Plotkin, Claire Jones, developed in her thesis a mature presentation of the probabilistic power domain for all continuous domains, but for all topological spaces and for continuous domains. For continuous domains, they have got a very, very elegant property. For a space X, any topological space, a continuous valuation on the lattice of open sets of X is like a measure, but is only defined on open sets. So it's like a measure in the sense that it takes the empty set to 0. So it's like a probability distribution, but it takes so it takes the empty set to 0. But because we can't talk about the difference of open sets and all that, so we can only have this axiom, which replaces the additivity axiom of probability distributions in a finite sense, that the probability weight of union of O1 and O2 plus the probability weight of the intersection of O1 and O2 is the sum of the probability weights of O1 and O2. So any probability distribution satisfies this. And so if this now is a continuous, Scott continuous function, it gives rise to what Clare-Jones called continuous valuation in this Licks paper by Jones and Plotkin in '89. The nice thing about this is that if we start with a domain, then the domain, a continuous DCPO, has got simple valuations, which forms a basis for what they call the probabilistic power domain. So first of all, what's a simple valuation? A simple valuation is essentially is the linear sum of point valuations, or Dirac measures, if you want. So we take a finite number of real numbers Qi and a finite number of elements of X, so this symbolically, this formal sum is defined as follows: that sigma of an open set is obtained by taking the sum of all the real numbers Qi such that Bi belongs to O. So it's a simple generalization of the Dirac measure, finite sum of Dirac measures for people who know what Dirac measures are, point measures are. So Clare-Jones showed that if D is a domain, if it's a continuous DCPO, then the space of continuous valuations, point-wise ordered, is a domain itself. And the simple valuations form a basis of this domain. This is a remarkable result. And also that they showed, following a categorical construction by Geary in the early 80s, that this functor P, that starting with a continuous domain D produces a probabilistic power domain P of D, is a commutative monad on domains. On the category of continuous domains. So I shouldn't say CCC, right? Cartesian closed category of continuous domains I meant here. So I have to make that correction. Together with one of my students and Saib Jahrumi, later on we showed, was that on continuous domains, probability measures and continuous valuations are in one-to-one correspondence. So there's no difference between them. And this makes the bridge between probability theory and universal semantics much closer in a sense. And then came this open problem. Are there any Cartesian closed category of domains that is closed under the power domain, probabilistic power domain constructor P? So the classification of Cartesian closed categories of domains is due to Achim Jung in a series of papers in late 80s and early 90s. For example, Scott domains is the classical example, but there are other categories of domains. One of them was discovered by Achim Jung. So there are no known CCCs, no Cartesian closed category of domains closed under the probabilistic power domain construction. This is the famous Jung-Tix open problem in '98, and this has remained unresolved. And so because the probabilistic power domain, in a sense, is like the power domain for non-determinism, except that it's for probabilistic computation, researchers had hoped that if we can find the CCC, if we solve the Hume-Higgs problem, so find the CCC that would be closed on the probabilistic power domain functor, would be closed on that, then that would lead to a domain-theoretic model for probabilistic computation, similar to power domains for non-determinism. But of course, no one could come up with a Cartesian closed category of domains closed under P. So in the absence of such a Cartesian closed category of domains, and because of the increasing importance of probabilistic computation in machine learning and deep learning and so on, researchers in the notational semantics, they resorted to other structures other than Scott domains and other than continuous DCPOs. So structures without an effective structure, structures which don't support a computability theory. So two prominent examples in recent years are by Mike Mislov and his, so Mike Mislov is one of the founders of domain theory. So this is Lick's paper in 2021 with his collaborators. And then there's a Journal of ACM paper by Jean Gopal-Larek last year. And they both have a common monad. They use the Cartesian closed category of DCPOs. They essentially give up on the way below relationship on the nice continuous domain structure of what has been used in traditional denotation semantics so far. And but the problem, even with just using DCPOs without any basis, without effective structure, is that they can't get a commutative monad. And to get a commutative monad, they had to restrict the probabilistic power domain constructor to a subset of that probabilistic power construction. So if C is a DCPO, then P0C, the so-called minimal valuations, is the smallest DCPO containing simple valuations on the DCPO C. So unlike a domain, P0C has no effective structure. Also, when you look at the monad construction, which is inherited from Giri's categorical construction in classical measure theory, the binding operation is quite involved in a sense, because from a function from a DCPO to this minimal valuations over another DCPO, you need to construct a function from the minimal valuations over C to the minimal valuation over C. And what this turns out to be for a given open set, you have to, well, you have got a function f, and you have got an element little c in C. So you have to, so FC would be a minimal valuation. You have, as little c varies over capital C, you have to evaluate this on open set O, and then integrate with respect to the probability distribution Q, which is given in this input P0C. So this is evaluating, in a sense, a kind of average of probabilities over a probability, which is generally non-computable. So there are other models for probabilistic computation in recent years. There has been a huge interest in probabilistic computation, but they use non-standard new techniques and new structures. So I've just mentioned two of them, two prominent ones: quasar Borel spaces There are several papers on that. I think this is a Nix paper and was followed by a Popple paper. And so quasi-Borel spaces essentially is a new structure which doesn't support computability theory, doesn't have basis in a sense. But interestingly, the monad construction has got some similarity with what we have, although the structures are quite different and quite new. The monad construction has got some similar ideas in the construction of monads that I will introduce in a minute. So, and also the probabilistic coherent spaces, this goes back to Girard and his linear logic. So one prominent paper on this is by Danos and Erhard. So again, these are non-standard, they use non-standard spaces and structures. So I'm not going to have time to go over them. Right, so now we come to the subject of our approach and our proposal. So we argue that the natural approach to probabilistic computation is as follows. So first of all, Scott domains provide the basic and elegant structure in modeling non-probabilistic computation very successfully. And open sets and as observable events or semi-decidable events, they were promoted by Mike Smith, Samson Abramsky, Steve Vickers, and Achim Jung. So Vickers has got this famous book, Topology by Logic. Abramsky has got this famous paper, Domain theory in logical form. Essentially, we think of open sets as semi-decidable predicates. And in terms of probability theory, for us, these are the events. So instead of having a sigma subset of measure of subsets, we have got open sets as events. And random variables from standard sample spaces and probability spaces to Scott domains, they capture probability distributions as axiomatized by Kolmogorov. And here is the important connection, because a random variable is essentially a function, from the probability space to a domain. Therefore, it is aligned with the paradigm of functional programming languages, aligned with non-determinism in dimensional semantics. So it's a function from a space to another space. Whereas a probability distribution on a space is not a function on the space, it's a function on the open sets or on the measurable sets or the sigma algebra of sets. So that's why we think it's more natural to use random variables to capture probabilistic computation rather than probability distributions per se. So a simple data type for probabilistic computation is provided by random variables on Scott domains with an equivalence relation on random variables, because as we said, two random variables can capture the same probability distribution. So random variables should be defined up to equivalence. So we have this notion of equivalence of random variables that we need to carry with us. So there's this representation theory for probability distributions on Scott domains, and this is the key result that is the basis of our work. So take the probability space A, either the Cantor space or the unit interval with a uniform probability distribution nu, as I introduced earlier on, and let D be a Scott domain. Then the function space of, if you want, random variables from the probability space A to D is itself a Scott domain. So that's a very important observation. So by random variables, I mean Scott continuous functions from A to D, because taking open sets as observables and predicate transformers as the inverse image of continuous maps, this is the paradigm in domain theory in logical form that we work with. So we take random variables that are continuous, scope continuous functions. So now we work with the normalized probabilistic power domain of the Scott domain. So Claire Jones and Plotkin, they worked with sub-probability distributions, so sub-probability probabilistic power domain, if you want. So in the 90s, I worked on normalized, so real probability distributions on domains. So they have got some similar properties as those proven by Claire Jones. And we use these in this theorem. This is the basic theorem that take this map T, which takes a random variable on D. This is a Scott continuous map from the probability space A to Scott domain D. You take that random variable to the probability distribution that it induces, namely on any Scott open set O, it gives the probability weight nu of R minus 1 O. Whether we take the probability space to be the unit interval or the Cantor space is uniform. So T is a continuous surjection, so that's the theorem. And the surjection component of this property was actually proved by Mike Mislov in a paper on the archive in 2016 by using a sequence of pure maths results in classical measure theory and domain theory. So our proof is very elementary and very direct. And we also prove not just surjection, but also the continuity of this map, but also these other properties that T takes step functions that are the basic building blocks of this function space to simple valuations that are the basic building blocks of P1D, which is a continuous domain. Namely, T takes this step function to this simple valuation in a very, very simple way. So the simplicity of the preservation of the basis elements is key to the success of this model. And therefore, we can deduce quite easily that this mapping T is an effectively given map in two different ways. First of all, if you have got an effectively given, if you have got a computable random variable, from that we can effectively compute the probability distribution corresponding to that. But also vice versa. If you have got a computable probability distribution, we can go back and construct a computable random variable that is mapped to that probability distribution. But if we restrict our probability space, our sample space, to the open interval 0, 1, so instead of using the closed interval 0, 1, we use the open interval. Or instead, in the Cantor space, if we eliminate all sequences that end with infinitely recurring zeros, then we have got two sample spaces that with the Cantor topology are only locally compact, but not compact. And for these two probability spaces, this map T preserves the Weibull relation, which is a very desirable property because it will be an open map. So we have got now 4 canonical probability spaces, the closed interval, the open interval, and these 2 Cantor spaces. All right, so I have to hurry up a little bit. So now we talk about Scott domains with a partial equivalence relation on them to capture the equivalence of random variables. So a pair domain, so pair for partial equivalence relation, is a Scott domain together with a symmetric and transitive relation. It's a logical relation. A logical relation satisfies that the bottom element is related to itself, and for any increasing chain, di and d prime I, if di and d prime I are related, so is the list upper bounds. So random variables naturally form a logical relation. So this is well known in well, not in this name, but this is a well-known result content-wise in classical probability theory. So we do have a logical relation when we talk about random variables. So we take this logical relation and we use induction to extend this logical relation to all types, all higher types. So if you have got a paired domain, so we've got a Scott domain with a partial equivalence relation, which is not necessarily reflexive, then if you have got two functions, we say that f is equivalent to g if whenever two inputs are equivalent, then the corresponding outputs are equivalent by these two maps. And this gives us the morphism between two objects of the category as the equivalence class of such maps, pair class of maps. And then we can define the function space of two pair domains, D and E, with the equivalence relation DE, defined as the pair of maps. And similarly, we can define the Cartesian product of two pair domains. And then it's easy to show that the category of Scott domains enriched with pair is a Cartesian closed category. So now we define a random variable functor, a constructor on this pair category that constructs, given a pair domain, given a Scott domain with an with a partial equivalence relation, we construct random variables on it. So we need to define the R topology as a subset of the Scott topology on a pair domain. So D is a Scott domain, so it's got a Scott topology. The R topology is consisting of Scott open sets that are closed under the pair relation, on the partial equivalence relation, which means that if D belongs to an R open set and D prime is equivalent to D, then D prime also should be contained in the R open set O. So it's a very simple natural definition. And the R functor then is defined on the pair category as follows on objects. So if you have a pair domain D, the construction of random variables on this is given by we construct the random variables on D. So Scott continuous functions from our probability space A to D, together with this pair. And pair is defined, two random variables R and S are related if for all sample points omega in our probability space. First of all, R omega is related to R omega. So R sends any sample point to something that is related to itself, similarly S. And also we have got this property, which is similar to what a random variable, what equivalence on random variables is. So for any R open set, we want the induced measure by R and S to be the same. So nu of R minus 1 of O should be nu of S minus 1. So these are very natural definitions. And on morphism, also the definition is very natural. If you have got this equivalence class of maps from this pair domain to that pair domain, then R of F is quite simple. We just take a random variable R and then compose it with F here to get the equivalence class of maps that define R of F. All right, so now we turn the random variable constructor R into a monad. So for this, so take H to be a measure preserving or probability preserving continuous bijection for our probability space equipped with a uniform measure nu to the product of this probability space together with the product of the measure with itself. So we want a measure preserving or probability preserving continuous bijection on a set of full measure on A, right? And there are infinitely many ways of doing this. And the most natural way is take the Cantor space as the probability space. So for any infinite stream of bits, so split the infinite stream to its even part an odd part. So omega is split into its even part and an odd part. And this gives you the mapping that you want, the first component and the second component, the first projection and the second projection. So that's quite simple. This map is actually homomorphism. So it's bijection on the whole set. And this is very easy. For the unit interval, we can use the Hilbert space filling curve. I think I'm not going to have time to go over this, so I'm going to skip this. This is a very famous. It's more than a century old fancy continuous map. It's a kind of surjection from 0, 1 to the square, the unit square that is continuous, and it's almost everywhere a bijection. And there's a very simple representation of it using representation of numbers, real numbers in base 4, the quaternary representation of numbers using 4 simple maps of the unit square. They take, these are affine maps that just contract and rotate or reflect. They're very simple maps. And there's a domain-theoretic representation of this that we can use to get a better and better approximation to the Hilbert curve. I'm going to skip this. So now I'm going to come to the monad for probabilistic computation. So the monad, so the functor R from the pair category to itself has got natural transformations, unit and flattening. So these are very, very simple. So the unit takes an element D in the Scott domain D, and it just returns the constant map that takes any omega to D. So that's very simple. And the flattening operator, mu of D, is also very simple. It just splits the sample point omega to its first and second component by H1 and H2, either using the even and odd parts of omega if you're using the Cantor space, or the 2 components of the Hilbert curve if you're using the Hilbert curve, and just evaluate. So this is very simple. And also you can have a simple representation of the monad in terms of a Kleisli triple, and the dagger operator is also has got a very simple definition that just uses the splitting, uses H1 and H2. So these are very simple, but the monadic properties hold up to equivalence, of course. The important thing is that we have to take equivalence with us everywhere. And also these monads are both strong and commutative. So we've got 4 canonical monads. So there are infinitely many monads, but the 4 canonical probability spaces, they give rise to 4 canonical strong and commutative monads. I'm going to skip the details. Very useful monads are both strong and commutative, and this will be guaranteed in both cases if we have what is called these strength morphisms of this type, satisfying some conditions for the monad to be strong. So this gives a tensorial strength and a simple commutative relation to ensure that R is commutative. So in a very simple way, this map is the monad is both strong and commutative. Whereas if you look at the work of Mike Mislov and John, they need a kind of change of variables, Fubini's theorem for change of variables in multi-integration to ensure that there's a commutativity commutativity of the monads. And that's why, in fact, they have to use minimal valuations rather than just continuous valuations, because continuous valuations on DCPOs are not known to satisfy the Fubini theorem for change of integration. Anyway, so in our case, these are very simple, that the proofs are just a couple of sentences. So let me, so I think I still have a few minutes, right?
Yes, you can keep going. We're quite flexible, so finish properly.
All right. Well, I've come to the examples. So first of all, the one important thing about this work is that whereas monad is always useful in programming language, especially of course in functional programming languages, very important useful properties, in the probabilistic modeling using Scott domains that we have presented here, they have a unique feature in the sense that it is using the monads with which we can generate independent, identically distributed random variables. So the monad gives us a way of constructing independent samples from a random variable with the same probability distribution. That is quite remarkable. So first of all, if we use, if you have any probability distribution P on the real line R, and if you take the cumulative distribution of this probability distribution using inverse transform constructor, G, we will get a map which takes the unit interval 0, 1 to the domain of intervals. In fact, it maps the unit interval to real line except for a countable set of points at which the map is discontinuous, but countable number of points are not really important in theory of random variables and probability theory. But anyway, in terms of the domain theoretic presentation, we get a mapping from 0, 1 to IR, which is supported on the maximum elements of IR, namely on the real line. So this captures all probability distributions on the real line. And from any random variable on any Scott domain, D, we can get an independent, identically distributed random variables H1R and H2R. H1 and H2 are the two components of the monad. So by using the two components of monad and evaluating the random variable on them, we get two versions of the same random variable. And if we iterate this n times, we get 2 to the n independent identically distributed random variables, all equivalent to a given random variable R. And therefore, we can do sampling in a very easy way. So for example, there's a famous Box-Muller transform to use the uniform distribution on the unit interval and turn it into two Gaussian, two normal distribution on R. And the simple formula is this. So in our setting, so H1 and H2 are just the two components of the monad. We get two identical Gaussian normal distribution that are independent Z1 and Z2 using just the function cosine and logarithm. So that's quite simple. And for example, I'll give just one other example. If you have got n plus 1 identically distributed random variables Ri, then we just get the student t distribution of degree n as a mapping from the unit interval to IR by just taking this fraction. So that's quite simple. And now we can have functions of random variables. For example, the Dirichlet distribution. If you have got a finite number of real numbers alpha I, positive real numbers, and same number of random variables on the unit interval. And if we take if beta alpha is the vector representation of alpha I, the n real numbers, they give you vector alpha. B alpha is a real number in terms of the gamma function. Then the Dirichlet distribution due to Dirichlet is has got this distribution 1 over B alpha times the product of xi times alpha I minus 1. So we get a domain-theoretic version of this Dirichlet distribution by just taking the extension of this map into the domain of intervals. So we get a simple extension. It's a pointwise extension of the power map that we need, because here we are taking the power map for a fixed exponent. We have to take x to the power x to the power an exponent, and that's got a simple extension. Anyway, so we can capture this. So let me finish by saying that there are a number of directions of further work. One obvious extension is a simply typed lambda calculus for high order probabilistic computation with a constant for sampling and a basic Haskell implementation. And the hope is that we can have a very simple implementation in Haskell that can actually be used in practice. So a practical monad for Haskell. So another important part that I haven't had time to describe is conditional probabilities and Bayesian statistics. So in this framework, we can naturally capture Bayesian law and exactly define what is computable in conditional probability distribution and what is not computable in conditional distribution. And there's a lot of confusion about this in the literature. There's, for example, a Licks paper saying that conditional probability distribution is not computable. But in certain cases, including for continuous distributions, the Bayesian law is actually computable, and we can show this in practice. Then we can have expectation values of functions of random variables. So the nice thing about Scott domains, functions on Scott domains, is that when we want to integrate the expected value of a function of a random variable, so we have got a function, we've got a continuous function, and we've got a random variable, which is another continuous function. So using a Scott domain, both of these can be approximated by step functions. So you get a very simple way of approximating expected value of functions of random variables. And then, of course, this can be extended to a very general framework for probabilistic computation on Pauli spaces, namely complete separable metrizable spaces. So these are, for example, Banach spaces, examples of function spaces. So C1 function, C infinity function. So these are examples of complete separable metrizable spaces that are very important in function space theory, in classical mathematics. These are called Pauli spaces. So this can be extended because it can be shown that any Pauli space is the space of maximal elements of a Scott domain. So using this, we can have an extension of these results. And of course, we get a new model, a domain-theoretic model for stochastic processes. Thank you very much. Sorry if I went over the time limit a little bit. Thank you.
Okay. It's okay. We're quite flexible with the length of talks within a reasonable. We've got Pietro here. Is there anything you want to add? I understand you've been working with Abbas.
No, it was a fine presentation. Nothing to add.
Okay. You did okay.
Yeah.
Are there any questions? anyone wants to raise. I think you can just unmute yourself if you want to ask a question, because I think that's the easiest way. So if anyone wants to ask a question, please do so. Otherwise, I'll ask about, I mean, you didn't mention using proof tools in your further work. I mean, what do you think the most suitable proof tools might be to try and integrate this work into?
Well, that's a very good question. We haven't even thought about that. Yeah. So yeah. I think one thing that I should have mentioned this. So in the same way that we have got predicate transformers, there's a way of having a logic for random variables, so whether that's got some connection to proof theory, I'm not sure, but it's a very important area that we haven't embarked on yet. But it's something that, but I don't know. Maybe Pietro, do you want to say anything about this?
No, it's true that we haven't thought about this aspect.
Fair enough. I mean, I don't know if you could, as Hole and Isabel, it'd be a fairly heavyweight thing to put into something like that. But yes, certainly, I think maybe you can add it under future work for other people to look at rather than yourselves.
Good suggestion. Yeah,
future talks. Yeah. Any other questions anyone wants to ask? Margaret, you're always good for the question. Oh, Harsh. Okay, go ahead.
Yeah, I have some couple of questions actually. So there was a slide where you were mentioning the correspondence between the probability measures and the valuation functions. And I was wondering whether this can be stated at a more categorical level, because I understand that the Giri monad is a monad on measurable spaces, whereas the valuation monad, that is, I think, would be a monad on some on the category of topological spaces. So how is this, or what exactly is the correspondence exactly?
That's a very good question. I'm not sure whether anyone has looked into that. If someone has looked into this, it would be Jean. I don't know. I don't know the answer.
Okay.
But it's a very good question. Yeah.
Okay, I don't know ways. And the second one, actually, you presented a very nice duality when the slides related to representation theorem, because usually the duality, like stone duality, like you have the truth value object. So you look at predicates, which goes into, so these are maps going into some truth value objects. But here you are doing something dual, which is you are taking maps, which are random variables from your truth value object, which you usually denote A, to the space. And my first, so you define this random variable monad on the category of partial, I forgot the full, I'll just call it PER, pair. And so the question is whether you can define a similar monad on, let's say, just Scott domains, where you forget the equivalent structure, or even on category of measurable spaces, for example. So you
define the monad. You mean define the monad on just category of Scott domains?
Yeah. So like the way you define the random variable functor.
Well, I mean, the partial equivalence relation is essential to capture the equivalence of random variables corresponding to the same probability distribution. So if we don't use that, we have got a mishmash. It's not.
So maybe, okay, I see. I see your point. Yeah, there is a mismatch actually, but would it be natural to also, I guess, to consider these this definition over measurable spaces? So you fix some object like A, which is your Cantor cube or things like that, and then you look into the maps or random variables to the space, measurable spaces, and then see whether.
Yes, of course. Yeah, I mean this goes back to Kolmogorov. Of course, he may not have done this construction, but the definition of equivalence random goes back to him.
I
So
see.
I'm sure people have looked at this,
Okay.
but I don't know. We don't know the literature. We just started with these basic definitions and just built the construction from them. Later on, we discovered, for example, that Mike Mislov had proven one item of that fundamental theorem about the equivalence relation, the equivalence correspondence between random variables and probability distributions. So I think neither Pietro nor I initially knew a lot about the literature, the background literature on the subject, and we just learned our way through it.
Yes. Yeah, well, that's a good way. Thank you. Thanks for the presentation.
Thank you.
Any other questions or comments?
I was just wondering, you mentioned a Haskell implementation. How far are you away from being able to present that, and will it be made publicly available?
We haven't started that, but I think Pietro has started to develop the simply typed lambda calculus. So we have the rudiment of programming language for it, but not a Haskell implementation. Pietro, do you want to say more about it?
Yeah, now there are some library in Haskell implementing probabilistic computation, but essentially they are all based on the idea to model continuous evaluation in Haskell. And so the idea is that just to build a Haskell implementation where the fundamental notion is random variable instead of continuous evaluation, and see how it does work. It does work. Okay. Yeah, maybe.
Does that answer your question, Keith?
Yes, I'd be very, very interested to see it, because there's some interesting ideas I could discuss with my colleagues. I don't think I'm quite the right person myself, but I think there's some interesting stuff there to point my colleagues at, and I'd sort of be interested to have some sort of code or something like that we could show them.
Some sort of
code,
Cool.
some sort of a code base, you know, something sort of you can go around on a computer and look at, you know.
Yes, thank you.
I mean, the other tool we might be interested to look at this with is Mathematica. That's basically functional programming, and you know, you might just make it more mathematical possibly than with Haskell. Just an idea. You need a good Mathematica person to do it.
Well, I think I discussed this with Pietro, and the question is whether these libraries, they can cope with partial elements and recursion, or are they just libraries for total elements? So where, you know, probabilities are well defined rather than emerging as partial elements to better and better approximation, for example, when we do recursion. So that's the question, whether the existing tools can cope with, can capture partial elements or recursion. Anyway, we hope that this framework can capture partial elements and recursion.
Right. Well, I'm not a Mathematica expert, so I couldn't tell you whether it's a good thing to try, but it might, if you found one, it might be worth discussing with them to see how it might fit in. Okay. Any other questions or comments?